Hi, in this video I'll show you how to use a parallelogram to choose the right trigonometry for pretty much any forces problem. And by the way, do give it a look, even if you've tried using parallelograms before and decided you didn't like them at all. And this often happens. You might have decided that you prefer to stick with one triangle instead of two. And a single triangle can often be fine, and it is after all how you probably learnt to add and subtract vectors, as though the vectors are journeys, and then what we take to be the sum total of any two of them is just like going, as we say, as the crow flies, which is to say, a straight journey beginning and ending the same. And that's fine if it works for you, and if you never have any trouble deciding how to arrange the triangle. But with forces, that way the single triangle is missing a trick, which is that with a parallelogram you can always imagine the vector arrows as strings literally pulling, and in fact you draw them all as coming out from the same point, the same particle that they're pulling. And then it's totally natural and intuitive to see the middle string as having the same effect as the other two acting together. Imagine this one pulling at the same time this one is pulling. You know the particle will move roughly in this direction, somewhere in between. And then you can feel that the trigonometry is just going to make this more precise. Now you might have noticed a bit of cheek here. For a start, plenty of forces push, not pull. So that's a bit of poetic license. But also for the trigonometry to work as we feel it should, we must be pretending that the lengths of the strings depend somehow on how strongly they are pulling. Otherwise, how is trigonometry going to tell us the resulting direction of movement? And we don't normally make any such assumption. But yes, this is exactly what you do want to pretend. That you can see the strength of a pulling force in the length of the string pulling. And you'll find it's totally reliable, and you can feel sure that you've chosen the right trigonometry this way. Always sketch. It doesn't have to be a great sketch, something freehand or with a set square. Also go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. Question 3 is two forces given, and we're told the magnitude of the resultant. And we're going to use a parallelogram. We wouldn't have to. We could use an analogy with journeys. Here's a journey of 4 units. Here's another journey of 4 units. Just like that. If those vectors are identical, the resultant or overall total net journey is going to have a magnitude of 8. But if we were to change direction halfway through, it's plausible that that's 6. And we could put a vector from beginning to end, label it 6, and choose appropriate trigonometry. Fine. But there are, I would tend to think there are more advantages to using a parallelogram. But anyway, let's see how it works at least as well. This is our 6 Newton resultant, and here are the components which are 4 each. And this time, like this, we can see the forces as literally affected by actual strings pulling at the particle at the root there. A string pulling with a magnitude of 4, and another string here pulling with a magnitude of 4, we can see intuitively how the effect of that is going to be just like pulling on a string in this direction with a certain magnitude. With a right angle here, it's not going to be 6 actually, is it? It'll be 4 root 2. So let's put a break on those magnitudes there, and then let's see, we shouldn't have labelled it 6 yet, should we? Because it's going to vary all the way up to, we can see, a maximum of 8 down to a minimum of 0 when they're exactly opposed, the components, and anywhere in between. So there's about 6, and let's complete the parallelogram so that we can apply trigonometry on the same basis as before. We've just got 2 of these, of the triangle we had before. We want probably the easiest way in this case, because we've got 4 here and 4 there, we've got not only a parallelogram but a rhombus, so we want to take advantage of that probably and look at one of the 4 congruent right-angled triangles and see that this angle here, theta, let's mark it as well, that's going to have a cosine of 3 over 4. I could and perhaps should remove that 6, call it 3, and have two of those labels. Let's make the other one here. And there we are. So we can say that 2 theta, which is what they want to know, the angle between the 2 components, is going to be 2 of reverse cos of 3/4. And now let's find out what that is. 3/4 inverse cos 41.41-ish, so 82.82-ish. Or 82.8 to the standard 3 significant figures. Okay, and for part 2, we're looking at the effect of these 2 4-Newton forces on a particle. Well, they're going to act together just as the resultant. We can just think about the resultant acting on this particle at rest, apparently, on a smooth horizontal surface. So, failing, therefore, to push the particle left or right horizontally, so unless there are any other forces about to push left or right, but the other forces, what are they? A reaction force, vertical, and a weight, vertical. Everything's vertical, so we just need to see whether our combined force here of 6 newtons is acting vertically up or vertically down. And let's consider the other 2. mg, the weight acting down, and 3, the reaction force upwards. So either our 6 Newton force is acting in concert with the weight. That would be far too much, wouldn't it? In fact, it would already be too much even without any weight. Even were there no weight, the 3 Newton reaction force would be failing to cope with this pressure of our 6 Newton force. So it must be the other way around. our force is acting in concert with the reaction force. And so the weight must be balancing them, or they're balancing the weight, however you look at it. And we can see that mg must be 9, and therefore m must be 9 over g, or 9 over 9.8. Let's find out what that is. Right after fixing a few of these labels. So 9 over 9.8, 0.9184, and then finally they would just want to know the angle with the horizontal for either of those 4 Newton forces, but clearly that's just 90 minus theta. Let's call it phi, and phi equals 90 minus 41.41 or 48.59 or 48.6 degrees. 2, 3 significant figures. And there we are. Okay, question 4.